Okay, we're going to be looking at questions from the booklet. It's the stuff about breaking equilibrium by sliding and toppling. So here, let's draw a diagram for this question. We have this fridge, which is 80 centimeters in width. It has a weight of 60 G acting at its center of mass. It's on the floor, horizontal floor, and there's some normal contact force, friction, opposing this pushing force, okay, which acts at a height y. So the key to this question is to understand the following. If we're pushing, the contact force isn't acting at or directly at the center of the base anymore. So the contact force will sort of start to shift a distance x centimeters, x centimeters away from that point O that I've drawn, until we get to a stage where it will start to pivot or tip on the far corner when x becomes 80 centimeters. So as we push and this value x increases, if it gets to a stage where it's 80 centimeters, it will be on the point of tipping over. Okay, you can check this yourself if you sort of stand on the floor and change. Imagine someone's pushing you from behind and lean forward slightly. You can feel that the contact force with the floor sort of shifts from being on the center of your feet more towards your toes until you're about to topple over. Okay, so the fridge in this question will remain vertical so long as x is less than 80 centimeters. Okay. In these questions, we're going to find three equations. We're going to be looking at the vertical forces. In this case, we say that R is equal to 60G. And then we can also resolve horizontally. Now we're going to say that F is equal to the friction. And we're going to say that this force is equal to the friction because in all these questions we tend to think about increasing this pushing force until it's on the point of sliding. Okay, so on the point of sliding suggests that these horizontal forces are in balance. So we know the value for the coefficient of friction, so we can say that friction is 0.4 R, which is 24 G when you do the maths. Okay, so left is to take the moments about that point O that I've drawn. We can say that F times by Y for that moment plus the moment of 60 G times by 40 centimeters equals the moment of R times by X. Okay. So we could have an inequality here, but I'm just going to find the absolute maximum for all these values by substituting x to be 80 centimeters. So F times y equals R times x minus 60G times 40. When we do the substitutions, we get 60G times 80 minus 60G times 40, which is just 2,400G. Now replacing F by 24G gives us the following. So this here, when we divide by 24G, represents the maximum value for Y. Okay, so this is going to be the greatest value for Y, 100 centimeters or 1 meter high. We could have had an inequality there. So when we substituted the value for X in, we could have said F times Y is going to be less than or equal to 2,400G, which might have been a better way to answer the question. Okay, moving on. Okay, uniform loaded box of fish, etc., etc. So read the question, maybe have a go at the question first before you start following these instructions. If we draw this rectangular box, which is 90 by 15, it has a centre of mass and a weight acting at that centre of mass. It's got this tension force pulling it here, I've decided to draw it this way, and the contact force is going to be acting some distance away from the corner. If we resolve vertically, we get R is 200. Oh, sorry, let's take that back. We get R plus T root 2 over 2 for T cos 45 or T sine 45, however you want to think about it, equals 200. Resolving horizontally, you get the T root 2 over 2 equals the friction. And we know this because it says the tension in the rope is increased until the box starts to move. Okay, so we get the point where that horizontal force equals the friction. We'll take moments about this point O that I've drawn. So we say that 15 times T root 2 over 2 for that moment. And that's T sine alpha or T cos alpha, or sorry, T cos 45 or T sine 45, plus the moment of the normal contact force, which is going to be some distance x away, times by R, the normal contact force, and this is going to be equal to 200 times by 45 for that moment. Okay, we can say that the friction is equal to 2/3 of R, which you probably should have done earlier. If we then use this information to solve the horizontal and vertical forces simultaneously, we can say, rearranging the horizontal forces to get T in terms of R gives T is 2 root 2 over 3R, check you agree. This means if we substitute this into the vertical force, we get R plus 2/3 of R equals 200. So 5/3 of R equals 200, so R is 120. We're going to substitute this value of R and we can find the value of T. The value of T is just going to be 2 root 2 over 3 times by 120, or 80 root 2. So, carrying on, we're going to have 50 times by 80 root 2 times root 2 over 2, which gives 15 times 80 when you do it, plus x times 120, and this is going to be equal to 9,000. Simplifying gives 120x equals 7,800, so x is equal to 65 centimeters. Since this distance x, 65 centimeters, is not acting on the corner of the box will not lift off the ground. Okay, carrying on. So, next question, example 8. So again, pause the video, have a go at the question yourself, and then come back and check my solution. So we'll draw this chair from the side. We have the height 100 centimeters, the center of mass acting 20 centimeters from one end and 30 centimeters from the other at a weight of 50 newtons. We have this pushing force, and on both chair legs I'm going to draw a normal contact force and a friction. I'll call one of them A, one of them B, R of A, friction of A, R of B, friction of B. Resolving vertically, R of A plus R of B is equal to 50 newtons. Resolving horizontally gives P, the pushing force, equal to the sum of the frictional forces. Okay? We know this because the pushing force will be increased until it's about to slide. Okay, this we can say is mu times by 50, since the friction of A plus the friction of B will be mu R of A plus mu R of B, which is mu brackets R of A, R of B, which is mu times 50. Take moments about A. This gives 100 times P for the moment of the pushing force, plus the weight moment, because that will be acting in the same orientation, the same direction, so 20 times 50, and that's going to be equal to 50 centimeters times by the reaction force of B. So, we carry on, we can say that P equals 50 mu, so this is 5,000 mu plus 1,000 equals 50 times R of B. Okay, so if R of B is less than or equal to 50, then the chair will not tip. Okay, so if it's equal to 50, it will be on the point of tipping. But if it's less than or equal to 50, then there will be some force acting in A for the normal contact force there. So we can say 5,000 mu equals, or is less than or equal to, 2,500 minus 1,000, which is less than or equal to 1,500. So mu then is less than or equal to 3/10. Okay, so we've got this value of mu, and if we consider the pushing force going the other way, we can say the following. Here is a new diagram. If we take moments about A again, we can say that the pushing force times 100 is going to be bigger than the moment going the other way, because it is going to tip. So it's bigger than 50 times by 20 for the moment of the weight. So this gives 50 mu times 100 is bigger than 1,000, giving you mu is bigger than a fifth. So you get mu is between 0.2 and 0.3. Look at the next question again. Have a go at the question yourself before referring to this video. Pause the video now before answering the question. So let's draw this standard lamp on this slope. This is standard, we've done this before. So if we draw these lengths in, we know that it will be on the point of toppling if this line that I've just drawn is vertical. If this line is vertical, then it will be a similar triangle to the standard triangle that we draw. And so we can say this angle alpha will be equal to this angle alpha, which means that alpha will be equal, or tan alpha rather, will be equal to B over 2 all over H, which is equal to B over 2H. So that's what we're asked to show. Next, we have to show that mu is also equal to tan alpha. We do this by resolving horizontally and vertically. I haven't drawn forces, but I'll draw them in a moment. Resolving, when I say horizontally and vertically, I also mean perpendicular and parallel to the slope. So perpendicular to the slope, you get the normal contact force is equal to W cos alpha. Resolving up the slope gives the frictional force equals W sine alpha, since it's on the point of sliding. Mu we know is equal to friction over the normal contact force, so we get friction over normal contact force is tan alpha, as required. Continuing, let's add some stuff to our diagram for the second part of the question, this pushing force P acting at a height y. Now if we resolve perpendicular slope, we get the same thing. Adding some forces in. So R is still going to be W cos alpha. Resolving up the slope gives, this time the friction has been reversed because the pushing force will try and make it slide. So we get P is equal to the friction plus W sine alpha. We know that friction is mu R. We know that mu is tan alpha, which is B over 2H. And we know that R is W cos alpha plus W, and then add the W sine alpha. What I'm going to do now is consider what cos alpha and sine alpha are, since we know what tan alpha is. A good way to do this is to draw a triangle for alpha. We know that alpha, tan alpha is B over 2H, so we can draw this triangle here. If we find the hypotenuse, we get square root of B squared plus 4H squared. Substitute this for cos alpha and sine alpha. So B over 2HW, cos alpha is now going to be adjacent over hypotenuse, and then sine alpha is going to be opposite we're going to undo that. We're going to keep that sine alpha, sorry. Notice the two h's cancel and left with b over the square root of b squared plus 4h squared. And this is opposite over hypotenuse, so we get another w sine alpha plus the w sine alpha from before, giving us 2w sine alpha. Nice. Now let's take moments about the far corner where this normal contact force is going to be applied, since it's just going to be on the point of toppling. We know that the normal contact force will act in that corner. So we get the moment for the weight, or the weight components, the weight component perpendicular to the slope rather, which is w cos alpha times by b over 2. And this is going to be equal to the pushing force moment, which is p times by y. Ignore all this. Carrying on, we get w cos alpha times b over 2 equals y times by, we know what p is, it's going to be 2w sine alpha. Okay, so if we carry on doing the obvious stuff, w's cancel, divide through by sine alpha gives us 1 over tan alpha times b over 2 equals y. And so y is then equal to 2h over b times b over 2, which is just equal to h. Now this represents the highest possible value for the height, so we know that y must be below this level, else we know that the moment of py will be bigger than the moment of the weight component, so it will start to topple. Okay, carrying on. Next question. These questions are fairly straightforward. I think you can do them yourself and just check the answer at the end of the video. So we do the obvious stuff. We take vertical components for this question, giving us 150 plus 200 equals 250 plus f. So f then equals 100. Take moments about a to get x. This gives us 250 times 4 plus f times x equals 200 times 8. Doing the usual stuff, when you do the maths, you'll end up with x is equal to 6 centimetres. Okay, the next one is actually example 11 in your book. So I'm going to answer example 11 here. I just didn't copy the diagram to the right page. So example 11 asks us to find f alpha and the distance ps. Resolve horizontally and vertically. F sine alpha equals 12. Resolve horizontally gives 26 equals 21 plus f cos alpha. So f cos alpha equals 5. Now to find alpha and f, we don't actually need to take moments. We can just do a division. So if we do the vertical and the horizontal, do a division there, we get tan alpha equals 12 over 5. And so alpha equals the tan inverse of 12 over 5. I'm not going to do that, but you can check that in your calculator. And now to find the value f, a nice way to do it is to work out what sine alpha is from a triangle like this. We know that tan alpha gives 12 over 5, and so the hypotenuse of this triangle is going to be 13. So sine alpha then is going to be 12 over 13, so we can say that, and cos alpha gives 5 over 13. So sub in equation 1 gives 5 times 12 over 13 equals 12, so f is equal to 13. Another way to have done this without the triangles would be to say that we know that f sine squared alpha plus f cos squared alpha is going to be equal to 12 squared plus 5 squared. So f squared equals 169, so f is equal to 13 as required. Take the moments about s, and that will allow us to find ps very easily. So we have 4 times by the 26 is going to be equal to the 12 times by PS. So PS is going to be equal to 26 over 3. And so that's all the questions done on toppling and breaking equilibrium. Thanks very much for watching. Make sure that all your solutions are correct, and I'll see you next time.